we are working our way towards defining a function that allows us to initialize a neural network that is ready to learn. And in order to do that, I need to introduce a couple of APL primitives that we are going to use. And for that matter, in this video I will talk about Catenate, Transpose, Each, and Beside. So if you know these primitives, feel free to skip this video. Otherwise, I will start with explaining what Catenate does. And Catenate is actually, if I'm not mistaken, the same as concatenate, except that it means the same thing, but it's a different word, obviously. Except that it's just out of use nowadays, because concatenate is much more common nowadays. But it does exactly that. It concatenates two vectors. So if I have v1 and v2, and I use a comma, which is the glyph for catenate, I concatenate the two vectors. That's pretty simple, I think. If I have two matrices, let's say I have a matrix with 3 rows and 2 columns and it's filled with zeros, and then I have another matrix that has 3 rows and 4 columns, and it has the numbers 1, 2, 3, 4 repeated. This is M2. I can concatenate both of them, and the way it works is they end up side by side. And APL is array oriented, don't forget that. And so Catenate actually, or can work for arrays of arbitrary dimensions. So if you are interested, go ahead, pause the video, and read the tooltip on Catenate to see what happens with larger arrays or arrays that have different shapes. Then comes Transpose. Transpose is a very interesting and very useful primitive. And in its monadic version, what it does is, well, you can type it with APL shift 6, and you get this slanted symbol. Please don't confuse it with APL shift 5 for reverse. They are similar. What you want is the slanted one. And if you give it a matrix, let's work with M2, maybe it's easier. See, M2 has 3 rows and 4 columns, and it has the numbers 1, 2, 3, 4 laid out in the rows. And if you transpose it, what you get is a matrix with 4 rows and 3 columns, and every row here became a column in the transposed matrix. So that's what it does for matrices. Well, for vectors, transpose does absolutely nothing. Notice that v1 is a vector. But if I transpose a matrix with 1 row and 4 elements, then I get a column vector. So it's very important. Notice that 1, 4 reshaped v1 looks exactly the same as v1, but transposing v1 does nothing, and transposing the reshape of v1 gives you this. So be careful with that. Also, transpose also works for arrays of higher dimensions. It's just out of the scope of this series. So go ahead, pause the video, and do all the explorations you want until you become comfortable with this. Now we are going to talk about the operator each. If you recall, 1, 2, 3 plus 5 gives you 6, 7, 8. Because this plus 5, in a way, automatically maps over the vector on the left, because plus is a scalar function. And this works also if I type in, let's say, 1 to 3 plus 3 to 1. The plus is going to map over the respective elements, because plus is a scalar function. But not all functions are scalar. For example, the reshape function is not a scalar function. If I were to insert it, let's say in here, between the 1 to 3 and the 5, what I get is an array of shape 1 to 3 filled with 5s. And I can even check if the shape is correct, and of course it is. You just can't tell it apart from a matrix because the leading dimension is a 1, so maybe it's clearer if I change this to a 2. And so there you go, 2 matrices that are 2 by 3. So reshape is clearly not a scalar function because it doesn't have this mechanism of quote-unquote mapping over the arguments. But sometimes you really want this mapping to work. For example, let me create a vector of matrices. Let's take M2 and M1, and then M1 again, and then 2. So this is my vector of matrices. And let's say I want to find the shape of each of these matrices. Well, I can't do row VM because that's going to give me the shape of VM. And so I have to map row. And the way I do this is by saying I want to apply row to each of the elements of VM. These two dots over here, this is the each operator in APL, and you type it with APL 1, as in each one. And what it does is, it takes the function on the left, and it applies it over the elements of the argument on the right. So there you have it. These are the shapes of these matrices. Very well, but okay, let's say I didn't want the shape of these matrices. I want the shape of their transposes. How can I do that? Well, maybe the obvious answer is to map each one of the transposes of each one of the matrices. That works. That's also very inefficient because in a way you can look at each operator as an operator that allows you to loop over a vector, for example in this case VM, and so I'm looping once to transpose everything and then looping again to find their shapes. So I should really do it in one go, right? I think it seems reasonable. And so I want to say in some way, and we'll find out exactly how, that I want to find the shape after I take the transpose of each one of the matrices in VM. And what we replace with, or what we put in here, is actually the jot operator. You can type this jot with APL-J for jot. And this is basically function composition. So it takes these two functions and creates a single function, a derived function, that is the left one after the right one. And there you have it. It's exactly the same results as above. And so this is very helpful, not only when we want to make things a little bit more efficient, but also when we want to do tacit programming, which is something that's very interesting, but unfortunately out of the scope for these videos. And basically whenever we want to take two functions and bind them together to create a single function.